Okay, so we're basically done with the difficult stuff here. We just have the case where there's a limit ordinal in the subscript. So one of the neat things about Veblen functions is we can enumerate these functions to come up with new ordinals, and this also allows us to have infinite ordinals in the actual subscript. So let's say we have something like phi sub omega of 0 diagonalized at 3, for instance. This is a very, very simple case. We just follow this rule here, and this simply equals phi sub 3 of 0. So we just diagonalize this omega, and this turns into this. Very, very simple case. The next case would be when we have something non-zero in the input to the function. So phi sub omega of 1, for instance, and diagonalize this at 3. Now this is very simple, or very similar, sorry, to the third rule here. The only difference is we don't make n copies of this function here, basically. We just diagonalize the function. So we have phi sub 3, and then we keep the original omega function. So we have phi omega minus 1 from the inside here, and then add it to the outside to escape the fixed point trap. So very, very similar to this third rule, save for the fact that we just don't make n copies of this. Instead, we just diagonalize right there. Okay, so let's do an example that involves an infinite ordinal in the subscript. So this one might get a little lengthy, but it'll be a good opportunity to get another example in on how to do this. Whatever, more examples, the better with stuff like this, just because it's a little bit tedious, a little difficult to keep track of where you are, all your fixed points, when to do diagonalization and stuff like that. So let's do phi omega. Let's do this exact one, except we'll do it out full, whatever. Yeah, so this is just the very first step. So let's, guess I didn't need to rewrite it, but whatever, I'll rewrite it just for fun. Okay, so first step, same as before. Phi sub 3, phi omega of 0 plus 1. Okay. So where do we go from here? Well, now we can use the third step from the previous one because we have a successor. And we can break this apart into 3 copies of the phi 2 function, keep the inside of the function minus 1 from here, and then add it to the outside. So let's do that. We have 3 copies of the phi 2 function. We keep the inside phi 3 of phi omega of 0. We minus the 1 from here, so we just close the brackets and add it to the outside. Now let's break apart this phi 2 function into 2 copies of the phi 2 function, and then we'll keep the second one next to it. So we'll just have phi 2 copies of the 2 function of phi 2 of phi 3 phi omega of 0 plus 1. So now we can break apart this function here. So that's going to turn into 3 copies of the phi 1 function. We're going to keep the inside of the function minus 1 from here and add it to the outside again. So we're going to end up with phi 2, 3 copies of the phi 1 function, keeping the inside. So we have phi 2, phi 3, phi omega of 0 Sorry. See how easy it is to lose track? Okay. Close the bracket here because we're minusing 1 from the inside, and then we add it to the outside here of 3. And we keep doing the same kind of thing of keeping 2 copies of this function and then breaking one off. So let's do that again. So we have phi 2, 2 copies of the 1 function, break off of phi 1, of phi 2, of phi 3, of phi omega, 0, add 1. And we'll break apart this phi 1 into 3 copies of the phi sub 0 function. So we end up with phi 2, 2, 3 copies of the phi 0 function, phi 1, phi 2, phi 3, phi omega of 0 and we'll break this apart into two copies of the phi 0 function and then leave one off. So this phi 1, phi 2. I apologize for the tediousness of this, but it's important to get some examples in, so I think this will be beneficial. Okay, so we have this plus 1 inside the function that has phi sub 0 on the outside. So we'll do the same thing as we did before. We'll have this utilize this rule of exponents, and then close this bracket, and we end up multiplying this whole thing here by omega. So then we'll do this step here, just so we don't have to rewrite this. This omega then gets diagonalized to a 3. So we have 3 copies of this whole function right here. So then we can rewrite this as phi 2 of 2, phi 2 of 1, phi 2 of 0, phi 0, phi 1, phi 2, phi 3. And we'll keep 2 copies of this here, and we'll add the 3rd copy. So we have phi 0, phi 1, phi 2, phi 3 of phi omega. And because this will stay the exact same for a while, we can just rewrite this one right here, basically. So this phi omega of 0, now we can utilize this rule up here, where we basically just diagonalize the infinite ordinal that's in the subscript of it. So this turns into phi 0 of phi 1 of phi 2 of phi 3 of phi 3 of 0. Now let's just deal with this one right here, whatever, just so we don't have to keep on rewriting things. This phi 3 of 0 basically is going to apply to the second rule, I think, up here. Yep. Where there's a successor in the subscript, a 0 in here, and it's going to be n copies of the previous function. So this phi 3 of 0 is going to be 3 copies of the 2 function. Then we can break this apart into 2 copies of the 2 function, and then leave 1 copy out here. This will break apart into 3 copies of the phi 1 function, so we get phi 2 of 2 of phi 3 of 1. We can break off 2 copies and leave 1. And then this here breaks apart into 3 copies of the phi 0th function. So I end up getting this. And if you remember before, this here turns into omega to the omega, which can then be diagonalized into omega squared times 2, blah, 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 blah. So if you're so inclined, you can put this equation back together. I took little bits of it and broke it off just so we could kind of work on it without me having to tediously write this out and you having to watch me or whatever. So this is how you break apart something where infinite ordinals are involved with the subscripts and stuff like that. So the rules aren't much different. Once you get past a certain point, like, it's pretty much the exact same. The only different rules we really had were in the beginning when we diagonalize the subscript, and when we had to break it apart with something in the input right here. We had to diagonalize and then keep the function and get out of the fixed point and stuff like that. But it's basically the exact same rules as the bulk of what you're doing is using this stuff up here, and you use this just seldomly. So that's basically it for Veblen functions. If we were to go on from there, so make bigger ordinals than phi sub omega, I'll just scroll this over here a little bit. We're also allowed to put any previously constructed ordinals in, so we could do like phi sub epsilon naught, something like that. We can do phi sub zeta naught, phi sub eta naught. And we could even do other Veblen functions. So we could do like phi 0, 0, 0, 0, 5, 5, 5, blah, blah, blah. And we can even do an infinite nesting of Veblen functions, basically, like this. And this has a name. This is another ordinal. It's called gamma naught. And it's our first indeterminate ordinal. And the reason why it is because this is kind of like a function of functions. And the way we define something like gamma naught is built with Veblen functions with all zeros, basically. So when you think of it, you could really choose these numbers any way you want. Like there's nothing saying that you have to have zeros here, but it's more of an elegant solution if you assume that the Veblen functions are all built with zeros. So if, let's say, for instance, if you wrote down the fundamental sequence of gamma naught or whatever, you'd write it down as phi 0 of 0, which would be 1, then phi 0 of 0, then phi of 0 of 0 of 0, and so on. So just for fun, let's plug gamma naught into the fast-growing hierarchy and see what happens to this. So we'll use kind of our new terminology of the fast-growing hierarchy, having everything within brackets here. So let's do f gamma naught of 3. So this is going to equal the third element of the fundamental sequence, which is this here. So we're going to have f of phi sub 0 of 0, 0, 0 of 3. Phi 0, 0 is going to be 1. So we're going to have phi 1 of 0 of 0. Phi 1 of 0 we know is epsilon naught, so we can rewrite that as f phi epsilon naught of 0 of 3. Epsilon naught, as we know, diagonalizes to omega to the omega, and that diagonalizes to omega squared 2 plus omega 2 plus 3 or whatever. So let's just rewrite that in a couple, we'll do a couple steps at once here. Phi omega squared 2 plus omega 2 plus 3 of 3. So now what we do here is this follows the rule. Where is it? Scroll up here. This one here. So we have a successor in the subscript, and it's a function of 0 here. So this is as a successor because it doesn't have a fundamental sequence. So we can do 3 copies of the previous function, which would be this with just a 2 here. So we can write this out. And you know what? I'll just do this outside of the fast-growing hierarchy just so it's just so it's a little bit neater. So this turns into 3 copies of this function here, so just the previous function of 0. So now what we can do is we can break this apart into 2 copies of this, and then break the third one off. And then that one is going to turn into 3 copies of the previous function. That one's going to turn into 3 copies of the previous function, blah, 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 blah. So what you end up with is something like this. You end up with something like 2 copies of this function, and then 2 copies of the next function. It's going to be plus 1. 2 copies of the next function, omega 2. And you keep on going in this fashion. So basically you're making 3 copies of the previous function. You're keeping 2, breaking the next one off, and then using that to break that apart into the next 3 copies, and then so on and so forth. And you're going to get to a point eventually where you reach omega, and then it goes into the stuff that we've done before, basically. So you're going to have a huge a lineup of functions that are slowly decreasing until we get to something like this or whatever. So this is how you'd break apart something like gamma naught. So this is gamma naught is a huge, gigantic ordinal, as you can see. And even still, we can go further. No matter how big an ordinal is, we can always add 1 to it and get something bigger. But I'm going to save getting past gamma naught for the next video.